Section 4.3, Diagnostics on the Least Squares Regression Line. In this lesson, we want to be able to compute and interpret the coefficient of determination, perform residual analysis on a regression model, determine if a linear regression model is appropriate, and identify influential observations. In section 4.2, we discussed how to find the least squares regression line using formulas and technology. In this section, we present additional characteristics of the least squares regression line, along with graphical diagnostic tests to perform on these lines. Objective 1. We want to be able to compute and interpret the coefficient of determination. Now, consider the club head speed versus distance data. How could we predict the distance of a randomly selected shot? One guess might be the mean distance of all shots from the sample data, y bar, which is equal to 266.75 yards. Now suppose we were told that this particular shot resulted from a swing with a club head speed of 103 miles per hour. Knowing that a linear relation exists between club head speed and distance, we can improve our estimate of the distance of the shot. In fact, we could use the least squares regression model to adjust our guess to y hat, which is equal to 3.1661 times 103 minus 55.7966, which is equal to 270.3 yards. In statistical terms, we say that some of the variation in distance is explained by the linear relation between club head speed and distance. The proportion of variation in the response variable that is explained by the least squares regression line is called the coefficient of determination. The coefficient of determination, with the symbol of capital R squared, measures the proportion of total variation in the response variable that is explained by the least squares regression line. The coefficient of determination is a number between 0 and 1 inclusive. That is, capital R squared is going to be in between 0 and 1 inclusive. Now, if capital R squared is equal to 0, the least squares regression line has no explanatory value. If capital R squared equals 1, the least squares regression line explains 100% of the variation in the response variable. Okay, next, understanding deviations. Now, in the figure below, a horizontal line is drawn at the mean of y is equal to, or y bar, which is equal to 266.75. So let's go ahead and show that on our graph. So here is the mean line at y bar, which is equal to 266.75. Now, the predicted distance of a shot without us having any knowledge of club head speed. Now, if we know that the club head speed is 103 miles per hour, we increase our guess to 270.3 yards. So here is 103, and then we increase our guess to this point right here, where it's 270.3. Okay, so that's this situation here. Now, the difference between the predicted distance of 266.7 yards and the predicted distance of 270.3 yards is due to the fact that the club head speed is 103 miles per hour. So in other words, the difference between the prediction of y hat, which is equal to 270.3, and the mean value of 266.75 is explained by the linear relation club head speed and distance. So here we're saying that, in other words, the difference between the prediction of those two values is explained by the linear relation between club head speed and distance. So that means this is what we're talking about right here. This is the difference, deviation, explained by the club head speed. And again, that difference is the following values. Okay, so this represents the explained distance from 270.3 minus 266.75. And again, those are the y values here, and that's the y mean. Okay, now the observed distance when club head speed is 103 miles per hour is 274 yards. Okay, and that's what we have in our table. So the observed is at 103, then the distance is 274. So that means that here, the distance, or the observed distance when the club head speed is 103 per hour is 274 yards, is this particular point here. Okay, and so the difference between our predicted value of 270.3 and the actual value of 274 is due to factors other than the club head speed, meaning wind speed and the position of the ball in a club face, for example, and to random error. And so the difference just discussed are called deviations. So again, here's the difference between our predicted value and the actual value of 274 due to those factors. Okay, so we call this the difference deviation unexplained by club head speed. And that means that we're taking the following values for the unexplained. Okay, so the unexplained is taking the value of 274 and then subtracting the predicted value. So that means that this right here would then represent these two y values of taking 274 and then subtracting the predicted value of 270.3. Now, here are the three types of deviation. Okay, the type of deviation, the verbal description, and the symbolic representation. The total deviation, which is the deviation between the observed value y and the mean y value of the response variable. Okay, and then we have the explained deviation, which is a deviation between the predicted value and the mean value of the response variable. And then we have the unexplained deviation, which is a deviation between the observed value y and the predicted value of the response variable. And there is the symbolic representation of each. Now, in order to find the total deviation, okay, which is y minus y bar, it's going to equal y, the unexplained deviation, plus the explained deviation. So, again, let's take a look at that here. We know that we have the total deviation is going to equal the unexplained deviation plus the explained deviation. Okay. Now, although beyond the scope of this text, it can be shown that the total variation, which is the sum, is equal to the unexplained variation of this sum plus the explained variation. So dividing both sides by total variation, we would obtain 1, which is equal to the unexplained variation divided by the total variation, plus unexplained variation divided by total variation. And then subtracting the unexplained variation over total variation from both sides, we would get the following. We would get the coefficient of the termination, which is squared here, is equal to the explained variation over the total variation, which is equal to 1 minus the unexplained variation over the total variation. Okay, so again, let's take a look at the graph here to the right. The total deviation is the following. Okay, it's this entire scenario here. Okay, that is the total variation. Okay, when we take the value of y, right, so the total deviation here is the deviation between the observed value and the mean value. So that is y minus y bar. Okay, and then it's going to equal the unexplained deviation. So the unexplained deviation, which is a deviation between the observed value and the predicted value, where it's y minus y hat. So the unexplained is the following. Okay, we're taking the unexplained deviation, where it's y minus y hat. And then plus the explained deviation, again, which is the deviation between a predicted value and the mean value, which is y hat minus y bar. So here is the explained, and the explained, again, is y hat minus y bar. Now, again here, the unexplained variation is found by summing the squares of the residuals. So the sum of the residuals squared is equal to the sum of y minus y hat squared. So the smaller the sum of the squared individuals, the smaller the unexplained variation, and therefore the larger the coefficient of determination will be. Therefore, the closer the observed y's are to the regression line, which is the predicted y's, the larger the coefficient of determination will be. Now, how do we find? Finding the coefficient of determination. To find the coefficient of determination, which is capital R squared for the least squares regression line, y hat, which is equal to the slope times x plus the y-intercept, that is a single explanatory variable to the first degree, we square the linear correlation coefficient. That is, the coefficient of determination is equal to the linear correlation coefficient squared. This method does not work in general. However, for example, there are linear regression models with more than one explanatory variable, and these models are not covered in this course, however. Now, the caution, squaring the linear correlation coefficient to obtain the coefficient of determination works only for the least squares linear regression model with one explanatory variable. So, for example 1, determining and interpreting the coefficient of determination. Okay, determine interpret the coefficient of determination for the club head speed versus the distance data shown in Table 1. Well, let's recall what the coefficient, the linear correlation coefficient was. Okay, we found that R was equal to 0.9392. Okay, so what we did is we found the linear correlation coefficient by using this data. Okay, and so what do we do with that? Well, here is our linear correlation coefficient. And so in order to find the coefficient of determination, okay, we need to take the value of R and then square it. Well, the value of R is 0.9392, and then we're going to square it. And what that gives us is 0.882. And if we convert that to a percentage, we would say that it's 88.2% for the coefficient of determination. So what would we say then? We would say that the following, that 88.2 of the variation in distance is explained by the least squares regression model, and the rest, meaning 100%, okay, minus 88.2%. And so let me go ahead and rewrite that so that we know that when we subtract that, we're dealing with 100.0%, which gives us the 11.8%. And that means 11.8% of the variation in distance is explained by other factors.